Everything in the world follows the laws of physics. Ice is cold, fire is hot. Thin things tear, heavy things fall, and water flows downward. Everything else is an illusion, a distortion of perception. For decades, illusionists have built their craft on exactly this principle. The most famous stage magician of our time, David Copperfield, made the Statue of Liberty disappear in 1983. The effect was astonishing, and to this day no one knows for certain how he did it. Thousands of people stared into empty space and witnessed the impossible. But it was a trick. A brilliant one, but still a deception. The statue never went anywhere. People simply stopped seeing it. But what if there are things that need no tricks or stage sets? Things that baffle not only ordinary people, but science itself. Magic. No, this is our world, seen in a way we have never known before. Things that defy the laws of physics. We humans love to believe that we understand how the world works. Gravity pulls downward, light reflects, and material is either hard or soft or transparent. But the moment you look at these substances, our entire set of rules comes crashing down. Here is a material that absorbs nearly all light and disappears into the background, making everything it covers formless. Here is a substance that flows upward. Yes, upward. Don't ask us why. And here's a thread, invisible, as fine as silk, yet as strong as steel. These materials aren't from the future. They're already among us, and now we'll uncover their secret. Substances that defy the laws of physics. What we are about to show you is not an illusion, and that's the most important part. There are real materials and structures that genuinely exist, and even David Copperfield wouldn't envy their astonishing properties. Some might seem impossible to you, but rest assured everything is real and strictly follows the laws of physics. Clearly, there's more to this world than meets the eye. With that in mind, let's move on to the first item in our collection. At some point, nanotechnology experts came to wonder what would happen if you vertically aligned many carbon nanotubes and pressed them close together. How would such a material behave? The developers of Surrey Nanosystems were the first to come up with a practical answer. They created Vantablack, the darkest substance in the world. Vantablack is a honeycomb comprising of millions of carbon nanotubes. However, unlike in bee honeycombs, its carbon cells are empty. Although this structure is quite unique, its most important property is that it almost completely absorbs electromagnetic radiation. What does this mean? It means that it's possible to make an aircraft that doesn't reflect radar signals, optics without glare from scattered light, some new designs, and much more. Don't you see the implications? To fully understand Vantablack's effect, imagine being in an empty room with the ceiling, walls and floors covered in Vantablack. There's absolute darkness and void all around. You turn on a flashlight, but it doesn't make any difference. As long as the flashlight is pointing sideways, it doesn't light up anything, and you can't even see its beam. You might see your hand and legs when pointing it directly at yourself, but other than that, there's nothing around but a pitch-black void. If you pointed the flashlight ahead and took a step, you'd bump into an invisible wall. That's what 99.965% absorption means. Due to this property, we see any object with such a coating as shadowy anomalies against other objects. Its unmatched absorption makes it impossible to distinguish detail, see relief and shape. Any sculpture coated in Vantablack would be perceived as a two-dimensional silhouette made of black paper. Thanks to the ultimate black body effect, Vantablack has already found applications in aviation, car manufacturing, and of course, in space. What you've just witnessed was the uncanny ability of Vantablack to hide an object's texture, blurring the lines between reality and fiction. As impressive as this might be, you might want to hold on to your socks right now, cause we're about to knock them off. This stuff sounds totally like something ripped straight from a sci-fi epic. One of the most recurring motives in movies involving time travel and alien visitors is rapid wound healing and body regeneration. For now, these remain science fiction. However, the real evidence suggests that we might be seeing the dawn of such technology. You're about to see polymers capable of rebonding after being severed. Moreover, this reintegration neither involves loss of original properties nor any external intervention. Meet the PDMS SSIP BNB, an absolutely unique polymer with an innate flair for self-repair. Similar to futuristic robots, this material can seamlessly mend itself post-breakage without the need for adhesive, welding or any other tricks. Developed by scientists from Tianjin University, this elastomeric polymer has quite impressive resilience. It can regenerate even under low temperatures in fresh or seawater, and even in an aggressive chemical environment. While it's too soon to talk today about instantly regenerating human muscles and skin, this new polymer is sure to find applications in robotics, aviation, and automotive production. Imagine a car that can self-repair interior linings or a leather sofa fixing its upholstery all by itself. What's even more impressive is this polymer's ability to be transformed into a conductor by adding iridium and gallium. Just think about self-reparation electronics. What if you broke a smartphone in half only to see the two halves join together and merge within minutes all by themselves, turning into a fully functioning smartphone? The extraordinary properties of PDMS SSIP BNB push scientific achievements into the realm of sci-fi. While many modern materials astound us with their capabilities, we know that their production often involves complicated processes and sophisticated equipment. Fortunately, there are some exceptions where even the simplest processes can yield a super material. The discovery of graphene is one of these rare, almost magical moments in science. You might find it hard to believe that two young Moscow State University graduates equipped with cheap adhesive tape were the first to obtain graphene and subsequently even a Nobel Prize. Yet this is exactly what happened. In 2004, Andrei Geim and Konstantin Novoselov attempted to separate graphite into individual layers using adhesive tape. Multiple tape exfoliations later, they obtained a layer only 1 atom thick that one could see with the naked eye. This was the first piece of graphene. Further research revealed a plethora of graphene's unique properties. As it turns out, it's an excellent conductor of electricity and heat. And one could modify its properties by altering the shape of the sheet or substrate, which means an even bigger plethora of possible uses. Moreover, being 100 times stronger than steel, graphene is the thinnest and strongest material in the world. Now, this does sound unthinkable, doesn't it? Do you need an extravagant example showing its properties? Well, here's one. A 1 square meter graphene hammock can support a large cat weighing over 4 kilograms. Yet it would weigh less than one of its whiskers. Just for the sake of comparison, a piece of paper of the same size would be 100,000 times heavier. Given such unique properties, there is no doubt that graphene would revolutionize the production of electronic and optoelectronic devices, chemical sensors, nanocomposites, and energy storage systems. This chapter is about plastics. Let's start off with a simple question. What happens if you step on a plastic cup? You've probably visualized a crushed cup, right? That would be the case unless the cup was made from or coated with Line X. Finding it hard to believe? Well then, watch how a heavyweight stands on these cups. It's not easy to crush such a cup. It can withstand even more, and the cup doesn't even need to be entirely made of Line X. A thin coating on the surface would be enough. Line X is a particularly durable spray-on protective coating made from a 2-component polyurethane. In addition to its strength, it boasts high adhesion, chemical resistance, and abrasion resistance. Line X can fully protect virtually any surface. It might sound far-fetched, but even fierce axe blows would leave almost invisible marks on a car hood coated with Line X. And the coating would still be intact. Line X polyurethane materials are applied using specialized industrial equipment under high pressure. The sprayed material solidifies within 3 to 6 seconds. Its short curing time allows multiple layers of Line X to be applied without drips or runs at any desired thickness. New, groundbreaking materials never fail to surprise us with what was once considered impossible. In other words, every new technology strikes us with its novelty, and nanotechnology holds a special place here. Most people believe that the prefix nano implies something ultra-modern. Many would find it hard to believe that one of the most amazing nanomaterials was created almost 100 years ago. Nevertheless, it's true, and this material is known as aerogel. In the distant 1930s, American chemist Samuel Stevens Kistler was obsessed with one unique idea: to retain only the frame of a silicate gel, replacing its liquid with air. Using a clever and rather complex method, Kistler succeeded. Consequently, in 1931, he introduced the world to aerogel, a material with some outstanding properties. Aerogel consists of a 3-dimensional nanogrid with a framework of particles sized between 3 to 5 nanometers and cells up to 100 nanometers. As you've probably guessed, the cells are filled with air, which accounts for 99% of aerogel. Such a structure makes the material extremely lightweight and a solid insulator. You can easily hold 1 cubic meter of aerogel with your arm outstretched, and a millimeter-thick layer would protect you from a flamethrower. And you don't even need pure aerogel to shield yourself from a flamethrower, or any flame for that matter. It's enough to reinforce fiberglass with pieces of this material. Watch in awe as this person casually holds their palm against the wall made of this composite, even though a gas flamethrower is aimed at the other side. Aerogel's outstanding properties have earned this material 15 entries in the Guinness Book of Records. You have to admit that's quite impressive considering that the material was discovered 100 years ago. You already know graphene's capabilities and have just seen aerogel in action. Many of you are probably wondering what would you get if you tried to make aerogel out of graphene. It seems pretty tempting to combine graphene's strength and aerogel's lightness into one material. Well, Chinese experts already have a practical answer to this question. They've created the world's lightest solid material, graphene aerogel. With a density of only 0.16 milligram per cubic centimeter, its vacuum field variation is 7.5 times lighter than air. Without air in its pores, the material would simply hover. However, before you imagine anything crazy like a flying house, consider a few points. Although the idea of ultralight bricks sounds amazing, the vacuum-filled graphene aerogel quickly absorbs air and water vapor, making it heavier than air. Additionally, there's the challenge of enhancing the structural integrity of graphene aerogel bricks. Such research is ongoing and some prototype samples with promising properties have already been obtained. While they are heavier than air, their weight-strength ratio surpasses every known material. One major advancement happened in this field quite recently. It turns out that a 3-dimensional graphene matrix can be printed on a special 3D printer using unique carbon inks. These 3D printed graphene aerogels have some enhanced properties that are bound to revolutionize catalysis, desalination, as well as filtration and separation technology. You would see advancements in every field that requires large surface areas, low density, high mechanical rigidity, and specific porosity. This new material is so unique that it's hard to envision a full spectrum of its possible applications right now. The unique properties aren't the only thing that can surprise us when it comes to new materials. Some of them might surprise us just with their history. For instance, the story of starlight is so weird that it could be as well titled The 3 Mysteries of Maurice Ward. Mystery number 1. A regular hairdresser called Starlight, a polymer with an unparalleled thermal insulation properties in homemade conditions. Just watch how a raw chicken egg coated with a thin layer of Starlight remains fresh even when exposed to a blowtorch. But trust me, this goes far beyond egg preservation. One could coat a hand with a thin layer of Starlight, immerse it in molten steel, and still feel nothing. Starlight effectively protects objects against high temperatures. Moreover, unlike traditional materials like asbestos, only a thin layer is required. Another important thing is that Starlight is simply applied to the surface. There is no need to glue it or use any special fixation structures. You've got to admit that such material is indispensable for space exploration, aviation, the energy industry, etc. This leads us to Maurice Ward's second mystery. For some unclear reasons, the amateur chemist never revealed his secret. Neither agents from Boeing nor members from the UK's Ministry of Defence could strike a deal with him. Maurice Ward never sold the Starlight technology. He could have easily become wealthy and famous, but he chose to live on his own terms. The secret remained sealed and was taken to the grave. Now, you might ask, okay, that's indeed intriguing, but what about the third mystery? Well, here it goes. The public learned about Starlight in 1993. The inventor passed away in 2011. In 2013, ThermoShield bought all Starlight-related rights from Ward's family. Fast forward to our days, yet no one, not even ThermoShield or NASA's labs, has managed to replicate Maurice Ward's success. There's still no commercial product available, and this is the third mystery. We hope that one day science will unravel it, and we will see various Starlight applications. Despite all its amazing properties, the spotlight of our previous chapter Starlight couldn't dazzle anyone with external effects. However, shape-shifting nitinol is a totally different story. Just look at how it transforms. A nitinol paperclip can be bent or crumpled, but once slightly heated, around 40 degrees Celsius, the mangled wire transforms into its original paperclip shape. This looks mesmerizing. An experiment with a nitinol spring looks no less spectacular. Once stretched or crumpled, it becomes straight and elastic when heated. This nickel titanium alloy can remember its shape and restore itself when exposed to heat. Wondering how this happens? Let's tell you. The first thing you should know is that there are no nanoelectronics involved. Instead, the alloy has two structures, austenite and martensite. During deformation, austenite transforms into martensite at the bend points. When exposed to heat, the reverse transition occurs, thereby restoring the metal's original structure. Now, the true nitinol secret is that its memory can be fully erased by heating the alloy to 500 degrees Celsius. Nitinol's thermomechanical memory has already solved problems in multiple fields, including medicine, aerospace, and aviation. In medicine, nitinol fixators are applied to connect and straighten broken bone parts. Nitinol spirals restore the diameter of damaged vessels. In dentistry, nitinol arches have revolutionized bite correction. In space technology, nitinol produces self-sealing thermomechanical joints, self-straightening metal farms, as well as telescopic and parabolic antennas. In aviation, nitinol's memory has been used for variable geometry air intake devices and serrations on the nozzle's edge. In previous chapters, what surprised us the most were the material's physical properties or mysterious shape changes. But here, the very name of the substance stops us in our tracks. 3M dry water. It sounds, at the very least, contradictory since water can't be dry. But in reality, there's no contradiction. The dry water is actually perfluoro, 2 parts methyl, 3 parts pentanone, which looks exactly like water but has some completely different properties. Unlike regular water, nothing gets wet in dry water, not even cotton. The substance simply rolls off a paper napkin, leaving it completely dry. With such water, you can easily walk between the raindrops, pun intended, but it's also hard to dissolve anything in it. For instance, it doesn't mix with alcohol. The two liquids instantly separate, leaving a clear demarcation. We now know for a fact that dry water isn't really water. It's not drinkable, you can't clean anything with it. So how do we use it? Dry water is an excellent insulator. You can submerge a laptop in dry water aquarium and the device would still work. No issues with the keyboard. Dry water boils at around 50 degrees Celsius and evaporates rapidly without a trace. Naturally, it's perfect for extinguishing fires in server rooms, archives and museums. Electronics will remain intact, documents and paintings won't get wet. Dry water is quite fascinating, but it's not the only liquid that can surprise you. Watch closely how a ferromagnetic liquid behaves. This is arguably one of the most mesmerizing sights you can see today. It feels like its interaction with cylindrical and spherical magnets was taken straight from a world of science fiction and alien intelligence. The mathematically precise, yet unfamiliar, 3D shapes that form when the liquid contacts helical surfaces are especially mesmerizing. The dynamic visuals with surfaces appearing and disappearing all the same time are truly a joy to behold. Naturally, one starts to wonder how all of this works and why it happens. The answer might be easier than you think. In 1963, NASA employee Steve Papel was trying to solve the problem of delivering liquid fuel in zero gravity. Iron nanoparticles were added to the fuel, along with a small amount of surfactants to prevent clumping. A magnet was then used to draw the particles and consequently the fuel to the desired spot. That's it. This was the first ferromagnetic liquid. Now you know that liquids aren't just for show. Ferromagnetic fluids find applications in optics and electronics, as well as adaptive suspensions of supercars. Many beautiful experiments involve magnetic effects. Stay tuned for our next feature to see one of them. Magnet-related videos have become common these days, and they mostly involve metals. But what you're about to witness is a flat piece of graphite effortlessly levitating over a magnet. Everyone knows how challenging it is to place one magnet over another so it hovers in mid-air without sliding off. Achieving this manually is virtually impossible due to the shape of the magnetic field. However, you can easily do it with a graphite plate. What's more, the plate stays levitating even when nudged in any direction. What we witness here is stable levitation without any tricks. But how does it work? You might have guessed that the secret lies in the material of the plate. This isn't ordinary graphite, but pyrolytic graphite, an extremely strong diamagnetic substance. Its magnetic susceptibility is almost 40 times greater than that of bismuth, the best natural diamagnetic material. When exposed to an external magnetic field, the pyrolytic graphite generates its own magnetic field, oriented in the opposite direction to the former. The intensity of this inherent field depends on the external field's strength and the material's properties. Due to the pyrolytic graphite's unique qualities, the generated magnetic force can counteract the force of gravity. As a result, when repelled by an external magnetic field, a plate of this material can hover even above a regular, non-superconducting permanent magnet. You often need a strong magnet to show the extraordinary properties of materials. However, in the case of gallium, you can do without one. All you need is roughly 1 cubic centimeter of gallium, a couple of tablespoons of warm sulfuric acid, and an equal amount of potassium dichromate. Personally, using a magnet seems easier to me, but let's proceed with our experiment anyway. Introduce acid into a petri dish with gallium and see how the droplet of metal contracts. If you then add some potassium dichromate, the metal will start pulsating in a weird way. Gallium will contract and expand, pulsing at the rhythm of a heartbeat. This occurs due to the rare metal's properties. At room temperature, it remains liquid and readily wets most materials. In our experiment, the wetting properties are diminished by acid and are subsequently restored by the potassium dichromate. Consequently, the gallium droplet expands and contracts, caught in the tug-of-war between these chemicals. It's a pulsating metallic heart, a quite unusual sight. Gallium pulsation has multiple practical applications. It can be used to create chemical timers, microvalves, and mini pumps that operate without batteries. Gallium is also widely used in medicine, electronics, and electrical engineering. The average concentration of gallium in the Earth's crust doesn't exceed 0.002%, but it can still be extracted from mineral sources. Stay tuned to learn about the substance that never existed on our planet until humans invented it. Helium-2 doesn't occur in nature. It's a liquid created by humans in an attempt to reach absolute zero. While subjecting liquid helium to ultra-low temperatures, scientists noticed that it suddenly changed properties upon reaching a temperature of 2.17 Kelvin or lower. The changes were so significant that they called helium at such temperatures helium-2. This substance behaves very unusually. Let's see how. Superfluidity is the property of a liquid with zero viscosity. Being superfluid, helium-2 can permeate ceramics with pores as tiny as half a micron in diameter. No other known material can do that. There are two other experiments that vividly demonstrate this effect. If you pour helium-2 into a cup, filling it only halfway, you'll see a thin layer known as the rolling film crawling out of the cup's sides before dripping down. Alternatively, if you dip a capillary tip tube into a container with helium-2, a fountain of this superfluid will almost instantly eject from the tip. Helium-2 is difficult to store due to its superfluidity. It constantly tries to escape from a sealed container along the walls and through the tiniest gaps in the lid. This has to be taken into account in practical applications. The behavior of helium-2 at ultra-low temperatures is quite intriguing, but let's face it, unusual properties are not that unusual when it comes to such extreme conditions. Why don't we go back to the real world and take a look at, say, europium? This costly, rare earth metal belongs to the lanthanide group. In general, it shares many characteristics with its fellow lanthanides, but has one very distinct property. Unlike its chemical relatives, europium easily forms both divalent and trivalent compounds, meaning that it can bond with 2 or 3 atoms of different substances. This unique trait opens up 2 promising application avenues for europium. Divalent europium exhibits a stable red line in its emission spectrum as part of any compound. Such property is critical for developing organic red LEDs and phosphors based on it. This paves the way for eco-friendly photonics, where atmospheric carbon dioxide is used to produce light-emitting devices. Given the rising concerns about greenhouse gases and global warming, divalent europium-based technologies may offer a timely solution. In contrast, the emission spectrum of trivalent europium varies depending on the compound that incorporates its atoms. This property gave rise to an ingenious anti-counterfeiting strategy for the European currency. EU banknotes incorporate europium elements that glow in a specific spectrum. Replicating this glow demands precise paint formula, which makes it very challenging. Thus, europium ensures a high level of anti-counterfeiting protection. What we see now clearly challenges our everyday experiences. White sneakers remain clean after being in a muddy puddle, and Pepsi Cola rolls off a white t-shirt without a trace. Meanwhile, construction materials, tools, and car parts also stay clean, even when exposed to dirt and oil. As incredible as it may seem, this isn't a Photoshop trick, but the result of applying a hydrophobic coating. Hydrophobes refer to substances with non-wettable surfaces. Liquids bead up and don't get absorbed by such surfaces. This phenomenon is scientifically known as the lotus effect. Have a look at a water droplet on a lotus leaf. It takes on a spherical shape and rolls off without leaving any trace. This effect comes down to the special surface structure of hydrophobes. They have a micro-bristle layer that traps an air pocket beneath a droplet. In the case of lotus, this function is performed by ultrafine hairs, whereas artificial materials achieve it through micron-level texturing. Research reveals that most effective hydrophobic surfaces are micron-sized bumps layered with nano-sized protrusions. These materials are categorized as superhydrophobes. This kind of material is exactly what keeps the surfaces you see right now spotless. Now that we've seen how dirt fails to stain, it's time to explore the phenomenon of hot ice. Let's keep on breaking stereotypes. We're used to the fact that ice is cold. However, you're about to see one that can warm you up. If you'd like, you can even create an ice sculpture of Santa Claus in the summer. What makes it possible is the supersaturated solution of sodium acetate used instead of water. A tiny crystal introduced into the solution at room temperature triggers the crystallization, thus forming something of an ice cube. This process produces heat, making the ice hot. This effect is utilized in the manufacture of popular hand warmers. So the next time you need a quick warm-up, just use the ice. While hot ice may warm a car driver, sadly you can't use it to make a windshield. For that, you need robust car glass that doesn't shatter into pieces during a crash. In some cases, one needs even something more, specifically bullet-resistant glass. The bulletproof glass we see in movies is more than fiction and serves to protect people in real life. However, there's an important detail. The target remains passive and cannot retaliate with gunfire. It might seem like nothing can change this, but actually there's a solution. You will now see how one-way bulletproof glass works. Demonstrated by an employee of the Israeli firm BP Developments. A bullet from an M16 failed to breach the 2-inch thick glass from the outside. Yet the inner side remained completely unscathed. Yet when fired from the inside, bullets effortlessly go through. Notably, fragments of the exterior fly towards the attacker, improving the efficacy of return fire. The outer layer of this glass consists of hard, brittle acrylic. It is followed by thin layers of bullet-resistant carbonate with an adhesive layer of transparent, thin polyurethane, which helps to absorb the bullet's energy. When the shot comes from the inside, no energy is spent on pushing hard shards inward. Instead, the bullet merely forces the hard layer outward and flies along with fragments towards the enemy. In previous chapters, you've learnt about some intriguing substances with fascinating physical properties. Now, let's delve into something different. A substance that alters not its own, but our seemingly constant physical traits specifically. The pitch of our voice. Keep watching to see how a person's voice changes. Many of us probably remember from childhood how our voice becomes squeaky when we inhale helium from a party balloon. However, what you'll see now is actually the opposite. Watch closely as a woman inhales a certain gas that immediately deepens her voice. The same happens when a man inhales the gas.
Some of that.
And my voice gets really low, although somehow I'm still funny. It's scientific!
Notably, their pitches fully return to normal upon inhaling regular air. This indicates that the vocal structures haven't changed, so why did the voice alter? The reason lies in the unique physical properties of sulfur hexafluoride. This was the gas featured in the experiment. It has a very high density and is 5 times heavier than air, causing vocal cords used to regular air to produce a deeper, lower sound. There's another impressive experiment demonstrating its high density. If you fill an empty aquarium with sulfur hexafluoride and place a lightweight ship into it, it would float on invisible waves. Such a scene would never fail to amaze anyone. You've already seen the unusual behaviour of some substances with unique physical properties. However, even objects made from well-known and seemingly ordinary materials may act quite peculiarly. Now, let's take a look at a fascinating toy. The Celtic Stone. As suggested by its name, the Celtic Stone traces its origins back to an ancient artifact, first discovered in Celtic burial sites. For our demonstration, we'll use a modern replica, a commercially produced version of this item. If you spin the Celtic Stone counterclockwise, it simply rotates for a while, then gradually stops. In short, nothing out of the ordinary. The real magic unfolds when you spin it clockwise. The stone begins to wobble, then reverses its spin direction. This seems utterly counterintuitive, as nothing stops it or prompts it to spin the other way. Is this another quantum effect? Not in this case. The movement of the Celtic Stone strictly follows the laws of classical mechanics. The secret lies in its asymmetric mass distribution and instability along its longitudinal and transverse rotation axis. One can only wonder how the ancient Celts came up with such an ingenious toy. Stay tuned to discover even more mysteries. The gumbut is essentially a mathematical roly-poly or self-rightening object. It always finds equilibrium regardless of how it's tilted. The gumbut came into existence not in the lab but rather in the mind. The thing is, no such objects have been found in nature. Its shape is the result of solving a very complex topological problem. For a long time it was believed that a homogeneous convex object with one point of stable and one point of unstable equilibrium couldn't exist. In short, it was believed that a convex object that always returns to equilibrium should contain cavities or inserts made of a heavier material. A well-known example is the traditional roly-poly toy. The bottom part of this toy has a heavier insert, so whenever it's tilted, its centre of gravity never crosses the support point. As a result, gravitational force always makes the toy stand upward. Here everything is clear, but the question remains. Can we make a roly-poly toy from one material without any inserts or voids? Russian mathematician Vladimir Arnold was the first to propose that such objects could exist. The solution was found by Hungarian mathematicians Gabor Domokos and Peter Várkonyi. After 10 years of research, they even proved there could be multiple solutions to this problem. They also came up with the shape that you can see on the screen. As of now, there's only one physical type of the gumbut. No other forms have been proposed. Manufacturing such a toy is very challenging, requiring processing accuracy of about 1/10 of a millimetre. Yes, substances can really surprise us, but that's only the beginning. Now let's talk about the objects. Some of these objects and phenomena can be found in nature itself. Others are man-made. But do these things really defy the laws of physics, or is it just a myth? These things break every law of physics. Let's start with something simple. Square wheels can be considered as an unusual object that contradicts our common sense. The very name itself evokes a protest in our soul, disrupting the foundation of our life experience. The reason for this protest is the inertia of thinking. Since childhood, all of us see only round wheels. Indeed, almost everything created by man to move on land, cars, trains, tractors, motorcycles, bicycles, everything rolls on round wheels. Wait a minute, somebody in the audience might say. What about caterpillar vehicles? These are tractors, all-terrain vehicles, construction and military vehicles that ride on caterpillars, so we can do without wheels. That's a great question. Now you'll learn the answer and see that caterpillar vehicles also roll on round wheels. Take a closer look and you'll notice that the body of the crawler machinery always rests on small round rolling wheels. In fact, a bulldozer, a tank, an all-terrain vehicle rolls on them on its own steel road. Caterpillars. As we can see, the round wheel comes into the picture here too. As a result, everyday practice forms a strong logical chain in our mind. Land vehicles ride on wheels, wheels are always round. There can be no other wheels. Yes, we are convinced that there cannot be square wheels. However, this is where our usual logic fails. In science, such a logical fallacy is categorized as non sequitur. In this instance, it means that if we have not seen square wheels, it doesn't mean that such wheels cannot exist. The possibility of existence and practical application of square wheels was proved by a famous team of Mythbusters. They made such wheels and mounted them on a car. Do you think it drove? Those who answered yes would be right. Indeed, the car drove on square wheels. However, such a ride can hardly be called comfortable. Shaking during the movement is simply terrible. Some relief comes with speeding up, but still there are some very strong shakes. Naturally, traveling in such a car is not pleasant. However, it seems to us that square wheels have some advantages over round wheels. What do you think? Which wheel would provide better off-road performance when driving on mud, loose sand, deep snow? Of course, square wheels would win. Their angles would not let the car slip where round wheels are helpless. The important thing is that the car should have all-wheel drive. As a result, the things that we thought were impossible turn out not to be only possible, but also useful in some conditions. Let's move on to the next example that literally disrupts our everyday experience. It's so unusual that it may seem to violate the laws of physics. The power of the example is especially great because it involves a sense that is not easily fooled, the sense of pain. I think most viewers will agree with this. Yes, we know how easily our sights can be deceived and how often our hearing leads us astray, let alone the sense of smell and taste, because the things are so vague and fuzzy here. But it's different with our sense of pain. Our sense of touch is responsible for pain, and it functions quite reliably. For example, if some magician manages to give you the illusion that molten lead is cold, this illusion will be shattered once you touch the molten lead with your finger. You would feel the pain and pull your hand away. You can't fool the thermoreceptors. Now watch a man dipping his fingers into molten lead. He pulls his hand back quickly, then repeats the motion several times. The temperature of the molten lead is over 327 degrees Celsius, 620.6 degrees Fahrenheit. But nothing happens to his hand. There is no burn, and apparently the experimenter is not even in pain. How is that possible? Maybe it's some kind of deception, falsification? It would seem that according to all the laws of physics, even a short-term contact of the skin with a medium heated above 327 degrees Celsius, 620.6 Fahrenheit, should inevitably damage it, guaranteeing a severe burn with sharp pain. Let's watch the slow-motion video, and if there are any tricks, let's try to spot them. The slow-motion video confirms it all. The man really dips his fingers into the molten metal. On the screen you can clearly see the typical splashes. You can see the depth of the immersion. It's clear that the fingers do not have any means of protection. So what's the secret behind it all? Let's watch further and get the exact answer. The secret of the experience is the Leidenfrost effect. This is a physical phenomenon in which a liquid near a surface, the temperature of which is much higher than the boiling point of the liquid, forms an insulating vapor layer. The effect is named after the German physician Johann Gottlob Leidenfrost, who described it in his work, A Tract About Some Qualities of Common Water, in 1756. The temperature at which this effect occurs is called the Leidenfrost point. For water, it's approximately 193 degrees Celsius, 379 Fahrenheit. The melt temperature of the lead in our example is much higher, so the Leidenfrost effect is possible. In our example, it is water that the experimenter uses to create a protective insulating layer of vapor. Before dipping his fingers into the molten lead, he dips his palm into the water. Of course, this moment is not shown on the video to impress the viewer even more and create the illusion of contradiction to the laws of physics. By the way, the authors of this video know these laws pretty well. Pay your attention to the clean surface of the molten metal. There's no slag, impurities, contaminants on it. It's carefully cleaned of anything unwanted. Experimenters realize that if anything with a temperature above 300 degrees Celsius, about 600 degrees Fahrenheit, sticks to the fingers, then no Leidenfrost effect would help. The laws of physics are inexorable. They are always true, and sometimes they're used to create things that do not match our usual ideas about technology. You're about to see a great example of such a thing, but let's start with something funny from the life of the military. Jokes among military men are a regular thing, and sometimes soldiers are asked a question during moments of rest. You know very well that a shell from a cannon flies in a curved trajectory. So if you put the cannon on its side, can you shoot around the corner? Sometimes, to everyone's amusement, the answer is yes, you can. Of course, the idea of putting the cannon on its side to shoot around a corner sounds ridiculous, but it reveals the military's interest in such shooting. This interest arose with the sad experience of the positional battles of World War I and the street battles of World War II. Analysis of combat operations suggests that a curved barrel would give the shooter a great advantage when firing from a trench, from behind the corner of a building, etc. With such a barrel, his chances of hitting the enemy while remaining out of range of return fire increase. These chances may increase even more if the shooter can see what he's shooting at and has the ability to aim. Another application of the curved barrel was to fire at dead zones around the tank. For this purpose, the curved barrel should be mounted in a ball bearing on the turret and equipped with a periscopic sight. As you can see in the conditions of the First and Second World Wars, a machine gun with a curved barrel could perfectly complement the arsenal of an infantry platoon and increase the level of protection of armored vehicles. Realizing this, gunsmiths of the warring countries made attempts to implement the idea. From the technical point of view, there are two ways to do it. The barrel can be curved with loading and locking mechanisms, as well as the trigger mechanism remaining unchanged. Alternatively, the barrel can be left straight, but the weapon can be bent, making it fold up somewhere behind the barrel. Both methods, as always, have their pros and cons. A curved barrel wears out quickly, the bullets in it deform, the weapon is difficult to balance. At the same time, such a weapon is easy to put into production on the basis of existing serial models. Bending the weapon behind the barrel allows using a wide arsenal of standard ammunition, but requires solving complex technical and production problems unless we're talking about a primitive model with a curved buttstock. I wonder which option you'd choose, bending the barrel or bending the gun behind the barrel. Try yourself as a gun designer. In a minute you'll find out which option the history chose. Obviously, in war conditions it's easier to use the first option. That's exactly what Germany did in 1944. The Germans simply developed the Krummlauf, a bent barrel attachment for their famous STG-44 serial automatic rifle. Various models of the Krummlauf provided 45 degrees, 60 degrees and 90-degree barrel rotation, as well as 30-degree barrel lift. There's also a version of the MG42 and a tank version. Most infantry nozzles were made for the STG-44 with 30-degree tilt. The curved barrel nozzles had a very short service life, about 300 shots for the 30-degree version and 160 shots for the 45-degree version. The reason for this was the heavy loads on the barrel. In 1944, however, no barrels could save Nazi Germany. In the first post-war period, the Soviet Union showed the greatest attention to curved barrels. It developed the Goryanov medium machine gun with a curvature angle of up to 60 degrees. The Kalashnikov light machine gun with a curvature angle of up to 90 degrees for firing at dead zones of armored vehicles, and the Degtyaryov light machine gun with a curvature angle of up to 45 degrees for infantry. The barrel life was brought to 1,000 shots. Caliber of all designs was 7.62 millimeters. Curved barrels of larger calibers were not developed. In the West, there were no noticeable efforts in this direction. The new military doctrines did not envision large-scale positional warfare and street battles. However, the idea of firing around the corner wasn't forgotten. Its second version, with a bend behind the barrel, found application in special forces. The most promising example of such weapons is the corner shot system. It was developed by an Israeli Special Forces veteran. The weapon consists of two parts connected by a hinge. The maximum angle of bending is 63 degrees. The front part is fitted with a regular pistol with a straight barrel, a laser sight, flashlight and video camera. The second part is equipped with a buttstock, trigger mechanism, control panel, and display. The system is versatile. Not only various small arms can be installed in the front part, but also devices for firing with rubber bullets and tear gas grenades. What you've just seen proves one simple truth. It happens in life that a ridiculous idea, contradicting common sense, is suddenly implemented and becomes useful. This is where a curious point arises. We see that a man can invent a thing that should not exist, but in the end it does, and it's useful. But what about nature? Does it happen that we say, no, this is impossible, but it exists and lives beside us? I wonder how you answered that question. If you said yes, then you are right, and you're about to see one of the proofs in your rightness. Look, this is an alpine ibex, also known as the Steinbock alpine goat. At first glance, there's nothing remarkable about it. It cannot surprise with its size, bizarre colors, or the strength of its jaws. It has long horns, but in general, it's a peaceful herbivore. Ibex lives in the center of densely populated Europe, where it would seem that there is no wildlife left. The only place that hasn't been reached by civilization is the alpine rocks and gorges in the mountains of an altitude of 1,000 meters, 3,280 feet and more. But is it possible to live there? Who besides birds and insects can find a place on the steep walls? Can a four-legged mammal find food and breed there? Yes. Watch further, get answers, and see the impossible with your own eyes. In the process of evolution, the alpine ibex and its mountain relatives all over the world have learned to walk on almost vertical walls. Just look how they do it. For them, the death-defying moment on ledges as wide as a cash register receipt is just a normal family walk for a patch of grass. Or just look at this incredible scene. A she-goat and a baby goat are climbing up the huge flat wall of the dam. The terrible height doesn't frighten them. They find the smallest ledges and confidently move up. They only want to eat the salt exuding on the wall. After the meal, they'll descend. The sight of their descent is mind-blowing. Observing these movements unwittingly evokes admiration and amazement. Our consciousness protests it can't be. But we see it is, and our mind bursts with questions. How can an animal on hooves walk on walls at great height in any direction? How do they make their amazing jumps with sharp and precise stopping on spots where there is nothing even to catch hold of? What is the secret of such capabilities? The answers are already waiting for you. You're about to find out how skillfully mountain goats use the laws of physics without knowing anything about them. The main secret of alpine ibexes lies in the special structure of their hooves. They're arranged in such a way that they don't slip on smooth, highly inclined surfaces. The hooves are bifurcated into toes. They're sharp, narrow, and can pull apart greatly. At the bottom of each toe, there is a relatively soft leather sole, and on the outer edges there's a special protrusion, a rim, which is strong, rigid, but not as hard as bone. This arrangement provides a reliable grip on rocks. The hoof tissue regrows quickly so that the hoof is always in the right condition. The design is optimal, offering the best mechanics of interaction with the surface of stone, crushed stone, sand in various combinations. A surprisingly clever application of the laws of physics. The hooves of the ibex are an excellent tool, and it perfectly knows how to use them. Its skills have been refined by evolution, developed and strengthened by continuous training literally from the moment of birth. Nature has a knack of creating what seems impossible to us. You've just seen a couple of stories about how the impossible, in our opinion, can be possible and even useful. What about the opposite? Is there something that we think is possible, but the laws of nature say it's not? Does it happen that common sense, our practical experience say, everything is obvious, according to the laws of physics it must work? However, nothing works in reality. A vivid example of such contradiction is the story of perpetual motion machines. Now we'll show you two ingenious schemes of perpetual motion machines. They are simple enough, but guessing why they don't work is not easy. Let's start with a seemingly very simple water wheel. According to the inventor, the wheel should spin forever, and various useful equipment can be attached to its axis. The main component in the scheme is a capillary tube. Water rises through it, comes back to the blades of the wheel, drops on them, and, having spun the wheel, flows from the blades back into the vessel. The whole thing is then repeated. Note, if the power is not enough, the number of capillary tubes can be increased, and all problems with the load can be solved. You may agree at first glance everything is real. Water will certainly rise along the capillary. Anyone knows it. Getting on the blade, it will inevitably create a force to rotate the wheel, and so on. Everything seems to be right. But we are all educated people, and we know that nature will say no. It's impossible to create a perpetual motion machine. This is a consequence of the fundamental laws of physics. There is a strange contradiction. It turns out that according to some laws of physics, the water wheel is supposed to spin, but according to others, it's not. In fact, there is no contradiction. You just need to correctly apply the laws of physics. The point is that the force of surface tension, which raises the water on the capillary, will not let it flow out of it. So nothing will drip on the blades of the water wheel, and it will stand still. So the water wheel didn't work. Shall we try it with magnets? For example, the Macintosh wheel. The idea of a perpetual motion machine with a wheel and a magnet was patented back in 1823. The idea is also quite simple and beautiful. Look, we'll take a wheel with a groove inside and a steel ball rolling freely along that groove. We bring a strong magnet to the wheel, moving in the plane of the wheel perpendicular to its axis. The ball, attracted to the magnet, rolls up the groove and the wheel spins, the mechanical analog of a squirrel in a wheel. Naturally, according to the inventor, the wheel will spin forever until the magnet weakens or the ball is worn out. In fact, the ball will just rise a little along the groove and the system will stop in a position of equilibrium. There will be no movement. Nature will say no to another perpetual motion machine. Well, okay, but what about wheels and pendulums that spin for a long time? Shouldn't we believe our own eyes? Do not worry, in such cases your sight does not mislead you. You simply need to be sure that there is definitely a source of energy. It may be hidden, concealed. If there's no such source, then an external source is somehow cleverly used. It's definitely there. The laws of physics do not lie. People just can't get past the idea of a perpetual motion machine, and sometimes it leads to funny situations. A good example here is Heron's fountain. The description of this fountain, working without any pumps and without connection to any external vessels, came to us from ancient manuscripts. Heron's invention was replicated and demonstrated to the public. Part of the audience immediately mistook the toy for a perpetual motion machine. There's no doubt that even today, even among those who have understood the scheme of the fountain, there will be enthusiasts who will try to loop this scheme and turn it into a perpetual motion machine. Let's see what this famous fountain is. Let's find out how it works. The design basis consists of 3 vertically arranged vessels cleverly connected by tubes. The upper vessel is the bowl of the fountain. The bottom of the bowl is connected to the bottom of the lower vessel by a tube. If there's water in the bowl, there is a column of liquid in the tube, which, connecting with the liquid in the lower vessel, creates some air pressure above its surface. If the lower vessel is airtight, it will have a pressure equal to the weight of the column of the liquid. Heron's idea is to apply this pressure to the upper part of the middle vessel. It contains water too and will be pressurized as long as there is a column of liquid in the tube from the bowl to the lower vessel. Now this pressure should be utilized. To do this, a tube is run from the bowl from the nozzle of the fountain almost to the bottom of the middle vessel. Under the influence of air pressure, water rises to the nozzle of the fountain and it begins to work. It looks magical. There's no reservoir above the bowl, there are no pistons or mechanisms, but the fountain works. No noise, just a slight splash of water and that's it. The most important question is, how long can it work? The answer to this question will once again deprive the fans of the perpetual motion machine of any chance of success. With the correct starting setup, Heron's fountain works as long as there is sufficient hydrostatic column pressure in the tube from the bowl to the lower vessel. This means that with water in the middle vessel and the air in the lower vessel, the fountain will work as long as there is water in the bowl. However, water leaves the bowl faster than it comes in due to pressure loss and resistance in the tube's nozzle and also to evaporation. This difference will always be there, therefore the fountain cannot be looped and turned into a perpetual motion machine. We get another convincing proof that the laws of physics are inexorable. The idea of a perpetual motion machine was once very popular and caused a lot of hassle for scientists. Today, the idea of another sort of engine is attracting more and more attention. The consequences of its emergence will be no less tremendous. But unlike Perpetuum Mobile, the fundamental possibility of its creation is scientifically proven. In this story, we'll talk about warp drive. With its help, people will travel through space at speeds exceeding the speed of light. You may say it's impossible. It contradicts the fundamental laws of physics. I'd like to reassure the skeptics. A spaceship with such a drive moving at any speed doesn't violate the postulates of the constancy of the speed of light and the impossibility of its achievement by any material object. I know it's hard to believe, but the principle of warp drive operation is based on strict compliance with the laws of physics. And right now you'll learn what this principle is. Let's watch the video further to discover the wonders of space and time. The idea of warp drive isn't new. Back in the last century, science fiction writers actively used stories with starships warping space. By strongly compressing the space in front of it while stretching it out behind, the warp drive moves forward the region of space where the ship is in. Note, there is a kind of warp bubble of space moving forward. The ship rests inside this bubble and it's stationary relative to space here. So the postulates of the theory of relativity are not violated. The idea of warp drive gets around these postulates. Wait, so it's just science fiction, the distrustful viewer might object? You mean Star Trek and so on? Don't jump to conclusions. The idea of a warp drive ceased to be science fiction in 1994 when Miguel Alcubierre Moya published an article with a mathematical description of warp bubble space in the reputable and prestigious scientific journal Classical and Quantum Gravity. Since then, the fantastic warp bubble has become a mathematical object, Alcubierre bubble. In general, it's now proven that it's possible to build a warp drive, but it requires exotic matter with negative mass. If we manage to find such matter in the amount of 33 Earth masses, next to nothing, then we can consider building a warp drive. It's hard to say when humanity will have such technology capabilities. Nevertheless, let us hope that the fantastic drive will become a reality. Warp drive solves the main problem of space travel, but before we can fly to the stars, we have to get into space somehow. Today, we do that with chemical rockets. This technology is well tested, but it requires significant resources. The cost of delivering cargo to near-Earth orbit averages $3,500 per pound, 0.45 kilos. In the future, reusable rockets may reduce the cost to $50 per pound. But even at this cost, it's impossible to start intensive large-scale space exploration with launching hundreds and thousands of tons of cargo into orbit per day. The space elevator can radically change the situation. The idea is not new either. Konstantin Tsiolkovsky spoke about it back in 1895. For a long time it seemed to be a fantasy. But today, a number of companies in the US, Europe, China, Japan have already started to develop commercial projects of a space elevator. The design of such an elevator is approximately the same in all of the companies and consists of the following elements: base, cable, counterweight, elevator. In general, it looks like this. The elevator moves along the cable stretched between the ground base and the space counterweight in geostationary orbit. As you can see, it's all very simple. The main challenge is the cable material. The remaining elements can be manufactured today. The length of the cable should be at least 35,786 kilometers, 22,236 miles, because this is the height of the geostationary orbit. The length of the cable determines the capabilities of the elevator. For example, if we make a cable with a length of 144,000 kilometers, 89,000 miles, its end will fly in space at the speed of 10.93 kilometers per second. That's 6.79 miles a second. That's the escape speed for that altitude. It's needed to leave the Earth's orbit and fly to other planets in the solar system. We should dwell on this point for a moment. Someone might wonder how this speed is obtained. Let's find out. We know that the Earth rotates at a constant angular velocity and makes a complete rotation of 360 degrees in 24 hours. In one rotation, a point on the equator travels a path equal to the length of the equator. Now imagine that we have stretched a 144,000 kilometer, 89,000 mile long cable from this point in a radial direction into space. Its end rotates at the same angular velocity as the Earth. Can you imagine the gigantic distance it travels in the same 24 hours? That's how the escape speed is achieved. It's also possible to drop the cable from the Moon to the geosynchronous orbit of the Earth. Then the length of the cable would be about 362,000 kilometers. It is much longer than in options from the Earth, but the cable in this case would be significantly thinner and easier to manufacture. Obviously, in any case, the cable should be very durable and weigh as little as possible. Everybody already knows that it should be made of nanotubes, but so far the available materials provide only half of the required strength. Despite this, NASA experts believe that the concept of a space elevator is very promising. NASA even holds contests for the best model of the space elevator. That's how seriously the agency's experts treat this idea. According to their forecasts, Japanese and Chinese projects will be implemented by 2050. The cost of delivering 1 kilogram of cargo will then drop to $25. However, it's not that seamless. There are experts who consider space elevator projects difficult to implement. These include the famous Elon Musk. In particular, he claimed that this task is too complicated in technical terms. It's easier to build a bridge between Los Angeles and Tokyo than to erect an elevator to orbit. Despite such assessments, optimism still wins, and we hope that in a couple of decades anyone will be able to take an elevator directly into space for no more than $1,000. A space elevator can hardly be called an ordinary lifting mechanism, but you've seen that it is feasible and will be made one day. Some of you might then wonder what unusual ways of lifting loads have already been tested in practice. Don't rush to look for the answer on the internet. We've already prepared something interesting for you. Do you think it's possible to lift a car with an ordinary domestic vacuum cleaner? Many will doubt in reply, and rightly so. It's really hard to imagine such a thing, but nevertheless, it's possible. The effectiveness of such a method was tested by a famous team of mythbusters. To verify this hypothesis, they made 3 large suction cups, placed them on the hood, roof and trunk lid of a sedan. Then the suction cups were connected to the inlet of a domestic vacuum cleaner with the help of hoses. In addition, the suction cups were connected to a platform using metal rods. The platform was attached to the hook of the crane and the vacuum cleaner was switched on. The vacuum cleaner worked for some time, pumping air out of the suction cups. After the vacuum cleaner, as the experimenters believed, reached the limit of its capabilities, the crane driver switched on the lift. The car was lifted and the suction cups could hold its weight. What do you think the experimenters did to confirm the role of the vacuum cleaner? They turned it off. The car crashed down immediately. With the vacuum cleaner motor off, the air went in the opposite direction, from the atmosphere under the suction cups. The pressure differential rapidly decreased and the car broke loose and fell. The secret of the trick is in the large area of the suction cups. This is necessary because in pneumatics, similarly to hydraulics, the force is proportional to the pressure and the area of interaction. In our case, the force with which the atmosphere presses the suction cup to the surface depends on the technical capabilities of the vacuum cleaner and the suction cup area. That's why it worked out well with large suction cups and the experiment was successful. In the previous story, the application of the laws of physics does not cause any difficulties and the result of the experiment is easily predicted. But this is not always the case. There are quite simple cases where motion clearly contradicts the well-known laws of physics. A great example of such a contradiction is the paradox of a sailboat and a fan. Let's look at the diagram. You see a boat with a sail and a fan at the stern. Let's imagine the fan is turned on. What happens to the boat? Will it move? If so, in which direction? Many people think that the system is closed loop and blowing into the sail is like pulling your own hair. The boat is supposed to stand still. Indeed, the fan blows air towards the sail. This air jet has a certain amount of momentum. According to the law of momentum conservation, the same momentum, but in the opposite direction, is received by the hull of the boat. If there were no sail, the boat would sail backwards. But there's a sail. The sail meets the air from the fan, receives and transmits the received momentum to the boat's hull. This momentum is equal to the momentum from the fan, but it's directed forward. As a result, everything is balanced, and according to Newton's third law, the boat should stay in place. Surely the boat in the picture will not go anywhere. It will always stay in place. But in reality, it is different. In reality, the boat fan system is not a closed system. The boat can sail backwards, it can stay in place, it can sail forwards. There's no paradox in this, it all depends on the ratio of fan power to sail area. If the sail is small, then part of the air jet from the fan passes by and it doesn't give its momentum. As a result, the momentum of the fan is not fully balanced and the boat sails backwards. If we increase the sail area, at some value the boat will stay in place. The most interesting part, if we increase the fan speed with this sail, the boat will move forward. Forward movement occurs due to the fact that when the fan speed is increased, in addition to the increased jet momentum, a higher pressure is created at the inner surface of the sail. Under the influence of this pressure, the air, having given its momentum to the sail, slides on its inner surface and is thrown back, giving an additional momentum, pushing the boat forward. Furthermore, we should keep in mind that when the sail is filled with air, the resistance to forward motion is less than the resistance to backward motion. Yes, the reality is very different from the simplified scheme in the picture. Our next topic is also related to moving on water, but this time it will not be a boat, but a motorcycle that will move. Someone will instantly recall the special water scooters and wonder, what's so unusual about them? Yes, we can hardly surprise anyone with a water scooter nowadays, but we will show you something more interesting. Now you're going to see an enduro-class motorcycle rushing across rough terrain. There's no doubt about it, it's a true enduro. It's built for racing over bumps, holes, ditches, but what is it? It's jumping into a riverbank and it's not slowing down. Failed brakes, dirt on the glass and the rider can't see the river? Apparently that's the case. Look at this. The bike rushes through the shallow water, raising fountains of water and mud. There's depth ahead, we're sure. It'll all be over in a second, the heavy enduro will go underwater and hopefully the motorcyclist won't get hurt. However, something completely different happens instead. The motion continues. The motorcycle races along the surface of the river, beautifully ejecting jets of water from under the rear wheel. After riding across the river's surface, the motorcyclist heads towards the shore, rides out onto it, and stops. Now we can get a better look at the motorcycle. Could this be a new version of an amphibious vehicle? There are cars of this kind, so why couldn't there be an amphibious motorcycle? We can take a closer look and see there are no floats in the design. In the strong frame of the Enduro, there are no empty capacities at all, except for the fuel tank, of course. So, in full accordance with Archimedes' law, this bike can't float. So why doesn't it sink? Is it breaking the law of physics? No, our Enduro doesn't break the laws of physics. Yes, it can't float, but it can glide and slide on the water surface. For this purpose, it is equipped with small skis. The front wheel rotates in the slot of one of them. Two more are installed behind so that the rear wheel can rotate between them. The designers have not forgotten about the suspension system. A movable structure of aluminium arms provides stability not only during normal movement on the water, but also when jumping into the water from a springboard. Yes, after a jump, the bike doesn't sink, does not tip over, but quickly goes into glide mode. Figuratively speaking, we can say that the Archimedes law yielded to the laws of hydrodynamics, and we got a stunning show. The subject of our next story is much smaller and doesn't make a noise like an Enduro. However, its movement has long attracted the attention of serious scientists and their interest in it still has not faded. We're talking about the tippy top. It looks like a ball with its top cut off by about 1/5 of its diameter. On the plane of the cut, there is the stem of the top perpendicular to it. If we want to spin a tippy top, we should use the stem. That's exactly what will be done now. Watch carefully. Beyond any doubt, the difference between the movement of an ordinary top and its tippy top is fundamental. At first it spins like an ordinary top, then it gradually tilts on its side and the stem begins to make circles. The tilt continues, the stem touches the surface of the table, the top turns over completely and stands upright, rotating on the stem. The process of the tippy top overturning during rotation is amazing. Any viewer realizes that the top is much more stable standing on the ball than on the stem. This is easy to test. Swing the top in the usual position. It will return to its original position like a roly-poly toy. This is natural since the center of mass is lower than the center of the spherical part of the top. Now let's try to put it on the stem. It is impossible to do that at all because it is so unstable in this position. So it's clear with the balance in the resting position, but everything changes once the top starts spinning. Tippy top goes out of balance, tilts, and as soon as the stem touches the table, it flips over. Resting on the stem, it spins in a vertical position for a while until the charge of kinetic energy is exhausted. So, the top has flipped over and chosen the most unstable position, which is very strange. Our experience tells us that this is not how it usually happens, and everything tends to equilibrium in the most stable position. What's the secret? Why does the top get upside down? Some quantum effects again, mysterious fields? No, everything happens according to the law of classical mechanics. You only need to take into account the friction force at the point of contact of the top with the support. When the top rotates at the point of contact, the friction force creates a torque that raises the center of mass. In the tippy top, it is below the geometric center of the spherical bottom part. This torque tilts the top. At the point of touching the rotating stem, another frictional force is added, hence another torque needs to raise the center of mass. As a result, this center of mass rises to the maximum height, which corresponds to the vertical position with the stem at the bottom. Of course, the description of such motion without vector products of torque and angular velocities would seem unconvincing to someone, but let's not turn our video into a lecture on theoretical mechanics. The fact is that the unnatural motion of the tippy top occurs in strict accordance with the laws of physics. Yes, all these objects are astonishing. They behave differently. Not at all the way they're supposed to. Or so it seems. But what's truly weird is when something familiar, something ordinary, suddenly starts breaking the rules. When a fridge works without electricity. When a flying device uses neither wings nor fuel. These gadgets don't just ignore the laws of nature. It seems like they came from another world. Gadgets that defy the laws of physics? What did our ancestors view as the laws of physics when physics itself didn't even exist as a science? They actually had a lot of laws, and they certainly knew that one does not simply take off and fly. Yet eventually people did learn how to fly, and even in several ways. Flying devices can be generally divided into a few groups. Lighter than air devices, balloons, airships, and any other devices that use Archimedes, buoyant force. Heavier than air devices that rely on the lifting force of wings and or blades. Airplanes, helicopters, drones, and the like. Heavier than air devices that use vertical jet thrust, vertical takeoff aircraft, rockets, and any variations of such craft. One might think that it's impossible to come up with another method. And let's agree to keep some sci-fi technologies like anti-gravity out of the way. Not because they are impossible, but because we don't have such technology just yet. But then how can you explain this? If it's not anti-gravity, then what is it? Of course, if you're familiar with various technological tricks, you might not find it special at first. There are many videos online of metallic discs levitating over powerful electromagnets, often heating up in the process. However, a totally different principle applies to this, and it's astonishing once you understand how it works. Just take a look. This device is called an ion-propelled aircraft or lifter. It achieves lift using an ionic wind generated by the Biefeld-Brown effect. ionic wind. But we've agreed to keep science fiction out of this, you might say. In truth, it's not that complicated, but very intriguing and unexpected. Back in the 1920s, American scientists Thomas Brown and his assistant Paul Biefeld discovered an unusual effect. A certain force acted on a high-voltage charged asymmetric capacitor that was so strong that it could lift the capacitor in the air. The scientist initially believed he had found a way to influence gravity with electricity. The newly discovered phenomenon was given a fitting name: electrogravitation. If you look closely, you'll see a thin wire above the foil that plays a crucial role here. The voltage this wire gets is higher compared to the foil, tens of kilovolts to be precise. An intense electric field forms around the wires. There appears a coronal discharge that ionizes the air. Charged particles rush to the lower electrode and collide with air molecules, creating a significant flow known as the ionic wind. It's this wind that creates the force capable of lifting the structure into the air. Essentially, it's a form of jet thrust, but the way it arises is very unique. It looks impressive, but unfortunately the effect disappears in a vacuum as there's no air and nothing to ionize. It's a pity that the high voltage source is usually rather bulky. In many similar experiments, it's always positioned nearby and is connected to the lifter with wires. It's clear that the frame can only levitate within the tether's limits. However, there have been successful attempts to place everything on board and achieve an autonomous ion-propelled aircraft, which is quite impressive. This might seem like a new milestone in air travel, but of course there are still many issues with this flight principle. Imagine what an iron craft designed to lift one person might look like. A gigantic fragile structure the size of a tennis court, all under the voltage of tens of kilovolts. This doesn't seem like a good idea, plus it has very low efficiency. But just think back to the designs of the earliest airplanes and other flying devices, and compare them to what they looked like and how they operate now. Who can predict where innovation will take us and how such concepts will evolve in the next 50 years? Perhaps we'll finally get to see those silent flying cars from old sci-fi classics. Since the mass production of ion-propelled aircraft has still a long way to go, let's look at something more familiar. For instance, we're used to the back of the refrigerator getting warm. This is a normal side effect of the unit's operation, but how about the concept of a fridge that you literally have to heat up for it to cool things down? Sounds kind of counterintuitive, doesn't it? Yet such technology exists. Refrigerators that use this principle are called absorption fridges. They can indeed operate without any electricity. At first glance, it might seem like they defy the law of physics. But let's see how it works. First, let's recall how a standard compression refrigerator works. Its operation principle is based on a mechanical compressor turning the gaseous refrigerant into a liquid that converts back into gas inside the evaporator and directs it to a large coil condenser at the back of the fridge, where it's cooled by the surrounding air. The condenser and evaporator are separated by a valve that creates a pressure difference between them. In standard refrigerators, a capillary tube with a tiny cross-sectional area, for instance 0.2 millimeters, which is 0.008 inches, serves this purpose. The design ensures that only a very small amount of liquefied refrigerant can pass through it per unit of time. As a result, pressure increases in one part of the system, and the refrigerant liquefies. In another part, the refrigerant boils and evaporates, taking away heat and lowering the temperature inside the fridge. As you can see in this picture, absorption refrigerators operate on a similar principle. Just like that, the refrigerator is cooled using a refrigerant boiling in the evaporator. And just like that, a condenser turns the refrigerant into a liquid form. However, that's where the similarities end, and instead of a regular compressor, a so-called thermal compressor is used, which combines an absorber and a generator. In the absorber, the refrigerant, often ammonia, is intensively absorbed by water. This process corresponds to the suction stroke of a standard refrigerator compressor. Ammonia is highly water absorbable. For example, at 0 degrees Celsius, 32 degrees Fahrenheit, 1 liter, or 0.26 of a gallon, of water can absorb over 1,000 liters, 264 gallons, of ammonia. This water-ammonia solution then goes to the generator, where the solution is heated. Here, ammonia evaporates from the solution. This stage corresponds to the compression stroke in a conventional refrigerator. Although the absorption principle has been known for quite some time, using it to build a functional unit remained challenging for a long time due to some inherent contradictions. In the same gas circuit, the pressure had to be high in some sections and low in others. Moreover, a pumping mechanism had to be introduced. Although this seems relatively simple nowadays, engineers of that time couldn't achieve it. It wasn't until 1922 that Swedish inventors Platén and Munters managed to solve this issue. They took a very original and creative approach by introducing gaseous hydrogen into the system. This was the proverbial missing link that made such installations truly functional. Indeed, it's an elegant solution. The system contains no valves or compressors, operates quieter, and is much more durable compared to the standard compression refrigerators. This piqued industrialists' interest in such a device, leading to the active production of such refrigerators from 1922 and onwards. What's more, this type of refrigerator without any major modifications is still successfully produced today. Now that we've established that one can make a mechanical refrigerator, perhaps it's time to switch other household appliances to something more unusual. Just for fun, how about a mechanical TV set for a change? No way, it's too out there, this can't be right. Many people would say. And they'd be wrong indeed, the very idea sounds far-fetched. Not only does it seem to violate the laws of physics, but also common sense. However, in reality, neither is violated. In fact, mechanical TV sets actually existed in the early 20th century. Just to be clear, some electricity would still be needed, but only for backlighting, not for image scanning. That would indeed be done mechanically. In modern LED TVs and plasma panels, scanning is done electronically and each pixel corresponds to a specific signal. Old bulky TVs with cathode ray tubes used an electron beam for scanning. Electromagnetics physically deflect it, and it runs across the screen line by line. This happens very quickly, and our eyes perceive this rapid movement of a single dot as an image. Turns out, there's also a mechanical way to scan a signal that uses the so-called Nipkow disc. More than just a disc, it represents a foundational principle in early television technology. It is essentially the first mechanical image scanning device. It was invented by the German technician Paul Nipkow in 1884. Here's how it works. The disc has holes at varying distances from the center. When spun rapidly, the holes pass by a light bulb, and this is perceived by the human eye as glowing arcs and stripes merging into a small glowing area. Now, if you modulate the brightness of the light bulb with a signal, you'll get an image. This brings to mind a fun gadget that produces an impressive illusion of hovering, glowing numbers and inscriptions using a fan and LED strip. Only here the light source is stationary and everything relies on rotating holes synchronized with the designated flicker of the bulb. Such mechanical televisions were quite popular up until the 1930s. However, they had many limitations. The most significant and overwhelming was the resolution. For obvious reasons, such devices could display a maximum of 80 lines and on average only 30. Of course, no one was thinking about 4K 100 years ago, but still, 30 lines seems pretty depressing. What prevented increasing the resolution? Not physics, but common sense. To scale such a gadget's resolution to as little as 480 lines, one would need a disc that was 30 meters, 98 feet wide. This is hardly feasible unless you want to feature it in a myth-busting show. Since we're on the subject, let's have some fun and speculate on the size of the disc needed for a 4K resolution. Some enthusiasts have already done the calculations. 620 meters, that's 20,034 feet. That's 2 Eiffel Towers stacked up on top of each other. Indeed, this is where beloved steampunk would clearly hit its technological limitations. All right. If a mechanical television is a thing, what other strange and unusual stuff has humanity come up with that might just challenge our understanding of the laws of physics? To answer this, we can't help but turn to the legacy of a legendary man who epitomizes the triumph of human genius over the forces of nature. Of course, we're talking about Nikola Tesla. Surprisingly, we won't be discussing electricity, but rather water. Please don't be surprised. Tesla's genius went far beyond electric current. He dabbled in many other things. For instance, he came up and patented numerous inventions of varying utility. One of them is a remarkable example of an idea that's brilliant in its simplicity. First, let's make some things clear. What is a valve? It is a device that allows fluid or gas to flow in one direction and blocks it in another. Clearly, no pump, even the most natural one, like our heart, can function without a valve. Every valve should contain a movable element that rotates or shifts under the influence of flow, either opening or closing a passage. The shapes and designs can vary, but the principle is always the same. However, with Nikola Tesla, some things never work the way they usually do. He devised a mechanism with no moving parts that allows fluid to flow freely in one direction and blocks it in another. The trick is that the blocking force preventing the fluid from flowing is the fluid itself. The magic lies in the design of the device, the shape and the direction of the channels. When fluid flows in one direction, it remains undivided and laminar. In the reverse direction, it splits into multiple streams that counteract each other. The flow becomes turbulent, losing much of the fluid's kinetic energy, significantly decreasing the flow rate and creating a high resistance to the oncoming flow. The solution is quite elegant. The water blocks itself. However, in practice it doesn't work as one might imagine at first. Many enthusiasts have personally tried to replicate Tesla's valve, recording their results on video. So what do we see? Could it be non-functional? Is Tesla called a great illusion master for a reason? On the contrary, it works, but not in the way you would expect. Indeed, we see that the valve stops the water only briefly before it eventually finds a way out. But that's how this valve is supposed to work. It's actually designed for short-term flow blockage. So what's its practical application? Who could possibly need this? Many people could. This invention is genuinely effective in systems where the flow direction changes rapidly in a pulse mode. That is, the application of Tesla's valve is very specific. It can be used in micropumps or conversely in something more impressive like pulsating rocket engines. We've already seen quirky devices that can astonish you with how they work and what they can produce. Often you don't need complicated mechanics to achieve this. However, the most magical things that revolutionize our world happen in the field of microelectronics. We can't see these wonders with the naked eye because they are incredibly small, but we can describe them by interpreting complex formulas and calculations. Occasionally, the things you see in microelectronics are so unexpected that you can't help but stay in awe. For instance, when talking about gadget memory, most people would imagine this. IT specialists would probably see something like this. But hardly anyone would even remotely think of something like this. And yet this, too, is memory. But how? Why does it look like this? How does it function? Does it really work? You're about to find out. This is the so-called ferrite core memory. While it may seem like an exotic relic now, there was a time when such memory was the pinnacle of progress. So what is it? It's precisely what you see, an array of metallic rings with wires threaded through them. The passing current magnetizes the rings in one direction or another. And that's it, you have zeros and ones, the binary numbering system. Moreover, just like in modern gadgets and computers, there are both rewritable and read-only memories. In the former, the rings magnetize when the current flows through the wires. In the latter, the rings are pre-magnetized, allowing the current to read but not re-magnetize them. Magnetic ferrite core memory devices consisted of comprised units with numerous ring magnets arranged in orderly rows in the form of a flat or spatial grid. In a full memory block, there could be up to hundreds of thousands of them. The cores were mostly 1 to 5 millimeters, 0.008 to 0.2 inches in diameter, and in the most advanced machines, the minimum diameter reached 0.25 to 0.30 millimeters, 0.1 to 0.012 inches. You see, there was a race back then, just as there is now. The only difference is that now it concerns extra nanometers in microchips. Naturally, we see it today as an incredibly bulky, inefficient, and potentially glitchy structure. It even looks like something out of Leonardo da Vinci's workshop. However, this technology was actually used on the Apollo spacecraft as part of the lunar program. And what's more, American shuttles employed such, well, electronics up until 1991. Let's shift our focus from exotics and explore another memory type that surprises us with the sheer fact that someone ever thought of such an idea. This is memory based on an electron beam tube. This is another quite old gadget which is called the Williams tube. Its operation principle is very similar to that of bulky TV sets. An electromagnetic beam hits a phosphor, knocking an electron out of a cell. Only in this case, it's not done to show us the evening news, but to create a matrix of positively charged cells on the surface. This matrix will encode the required information in binary form. As one would expect, there are no fewer problems here than in the previously mentioned chainmail. At least, the very least, such memory had to be frequently refreshed due to rapid charge dissipation. Nonetheless, Williams tubes were widely used in the 40s to the 1950s, and there wasn't much of an alternative back then. By the way, you can really trace a whole technological evolution here. The first tube had a capacity of, wait for it, 1 bit. As the technology improved, the capacity increased to thousands of times that. If the Williams tube has failed to impress you, we have something special just for you. This is memory based on mercury delay lines. Just think about it. Mercury delay lines. The very phrase sounds ominous, so what exactly is this memory about? The functional part consists of a long tube filled with mercury and piezoelectric elements installed at both ends. One acts as a speaker, the other as a microphone. Hold on, what? What speaker and microphone are we talking about? We're discussing memory, right? Indeed we are. Keep watching and you'll be surprised more than once. The first piezoelectric element creates a sound wave in the memory. As this wave moves through the mercury, it retains memory. Yes, you've heard that right. As long as it moves, it retains memory. But what happens next? Then the second piezoelectric element reads it. If the information should be stored, it's relayed back to the first element, sending the wave on another round and creating a loop. Although it sounds simple, the implementation of the idea is still mind-blowing. Mercury, sound waves, and here's what it looks like. The entire setup might seem like a relic from a museum of useless inventions, or like something an eccentric engineer would come up with to prove some point. One can't help but wonder, why is it so complicated? Well, just because. Why not? Technological progress occasionally takes some whimsical paths. This memory, based on Mercury delay lines, only proves this point. However, it's riddled with challenges. The memory is not durable and needs to be constantly refreshed. There's no random access, only sequential, so high efficiency is something you can't even fathom. Mercury's temperature had to be constantly maintained at precisely 40 degrees Celsius, 104 degrees Fahrenheit. Any deviation would alter the speed of sound, throwing off all configurations. The memory needs very precise synchronization, and all of this consumes a monstrous amount of energy. Again, why would anyone need this? Surprisingly, despite its wildly intricate structure where literally everything seems excessive, it turned out to be more advantageous than the alternatives. Cheaper and more reliable than vacuum tubes, faster than relays, more durable than Williams tubes. As preposterous as it sounds, these devices were used up until the 1960s, right up to the dawn of the space age. Alright, we've seen some dinosaurs from the world of prehistoric electronics, and while they certainly didn't violate any laws of physics, they certainly show a rather peculiar application of these laws. But are we yet to see the most outstanding type of memory in the future? Absolutely, and we could take a sneak peek into this future. In fact, some of these ultra-modern devices seem to leap straight from the pages of sci-fi. Quantum memory immediately comes to mind. An invention that doesn't break the laws of physics, but rather bends them to their extremes. You'll hear more about that in a minute. As for promising memory types, there have been ongoing developments in the field. For instance, there's a holographic optical memory. Unlike traditional storage that uses a single layer of bits on a medium surface, this method stores data volumetrically. Does this ring a bell? In science fiction, mysterious crystals often appear as data storage devices. Who knows, maybe the future flash drives will look just like that. By the way, it seems perfect even in terms of bandwidth. Transferring data to such holographic media will be much faster than our traditional memory. This is because a laser can send modulated signals not sequentially, one bit at a time, but in a whole beam, and more importantly, a very large beam. This could potentially be 1,000,000 times faster than today's standards. There's also the so-called 5D memory, and no, it doesn't involve additional dimensions. Instead, this memory uses a medium with the tiniest elements that have 5 adjustable characteristics, namely 3 spatial coordinates, polarization, and transparency levels. This is what allows us to vastly scale up such memory. There are many more memory options, some quite unexpected. Quantum memory particularly stands out among these innovative storage methods, seemingly challenging both physics and logic. Let's go back to it. Quantum computers. You've likely heard of them countless times, and many of you even have a working knowledge of how they operate. So let's dive right into it. Given that we have quantum computers, it stands to reason that there should be quantum memory, right? It would only make sense if there was one. Even though quantum computers differ drastically from our traditional ones, the general idea is still the same. A quick reminder for those who need it: the magic of quantum computers begins with the fundamental principles of their operation. Traditional memory has cells, each encoding either a 0 or a 1. However, in quantum memory, each cell encodes both states simultaneously, both 0 and 1. This isn't merely a metaphor, but a direct result of quantum mechanics. This phenomenon is known as superposition. Think of Schrödinger's cat, which is simultaneously dead and alive. That's the concept at play here. Such cells are called qubits or quantum bits. Physically, these could be superconducting loops with a current circulating in both directions at once. Or they could be ion traps, where a particle exists in 2 places simultaneously. The main thing is that you can encode a combination of 4 states with 2 qubits, 8 states with 3 qubits, and so on, exponentially. Over a quadrillion states can be stored in just 50 qubits. Essentially, that's over 1,000 terabytes in just 50 cells. This definitely seems to challenge not just the laws of physics, but also mathematics. How does all of this work? Well, that's a topic for another day. Quantum computers are at the forefront of science, where humanity closely interacts with the fundamental laws of the universe itself, the very fabric of what is all around us. Since we are on the subject of gadgets, let's consider something that we most closely associate with this word. After all, it's only natural to think about a gadget as something compact we carry with us. Let's imagine our descendant from the distant future visiting us today. What would he wear on his wrist? What could the wrist gadget of a future traveler look like? Setting aside fantastical ideas like handheld teleporters, an atomic wristwatch seems quite plausible. This may come as a surprise, but something similar already exists. At least, we're not that far from such technology. Of course, we're not talking about watches with a miniature atomic reactor. That would be too out there, even for the science fiction. This is not about radiation at all. There's none, because these devices would operate based not on nuclear decay, but on processes involving electrons in atomic orbitals. This doesn't result in any dangerous radiation. Here's how atomic clocks function. We take a suitable substance, usually rubidium or cesium. Then we evaporate it and pass microwave radiation of a specific frequency through the resulting gas. Electrons absorb this radiation and move to a higher energy level. These levels are selected so that absorption occurs when the frequency precisely matches the pre-calculated value. The slightest deviation in either direction nullifies the effect. Sensitive sensors monitor the absorption of microwaves, and a feedback system adjusts the radiation frequency so that it always matches the set one. This standard is then used to count seconds, minutes, and so forth with great precision. One of the main advantages of such devices is that they can be compact. Even the most basic models can be placed in a small case which would easily fit on an extremely precise navigation satellite. And if a visitor from the past needed such precision, we would have some good news for them. Even now, we have super compact atomic clock models smaller than a matchbox. They contain a capsule with the working substance just a few millimeters in diameter. Instead of microwaves, we use an infrared laser modulated by microwaves. To measure absorption, these devices simply look at the transparency instead of separating excited atoms with a magnetic field, forming a beam, and so on. As a result, while the accuracy of these miniature atomic clocks is slightly less than their larger counterparts, they remain impressive. While the most accurate quartz watches deviate by 1 second in 2 to 3 months, miniature atomic ones would only err by a second every 600 years, spanning multiple generations. Indeed, there is no magic here, no tricks. All the substances, objects, and devices you've learnt about today are part of our reality. And while they may seem to defy physics at first glance, in truth, they simply remind us how much we still don't know about the world.